Let's continue with part 3 video of lecture 5, chapter 6, control charts for variables. There are two phases or purposes in statistical control, statistical quality control or process control. First, we remove special causes of variation or assignable causes of variation. They're the same through hypothesis testing and Ishikawa tools application. Then, so the first step are the yellow ones here showing in this picture. Then second phase, we manage the process with control charts to improve the process, stabilize one process, and have confidence in when to act. And here are the steps, blue ones on this picture. There are connections between hypothesis tests and control charts. Since we are learning both of them, we need to identify their similarities, correspondence, and differences. So a control chart is like a sideway hypothesis test. When there's a shift in the process, it may indicate the test statistic falls into the rejection region of a hypothesis. We can avoid heads of costly errors by detecting trends in time if we use control charts. Let's review hypothesis test and see how it relates to control chart. A statistical hypothesis is a statement about the value of a parameter from a probability distribution. For example, use a sample of data to test if the mean equals to mu0. And if the process is in control, the mean should be mu0 or not too much different than mu0. The null and alternative hypotheses are stated like this. If the null is accepted, then we conclude the process is in control. Otherwise, the process is out of control. To test the hypothesis, we take a random sample from the process and compute the test statistic. Based on type 1 error probability alpha, we find the critical values. If it's a two-sided problem, there are two critical values, asymmetry to the mu. Here they are the positive and negative z half alpha. Compare the test statistic with the critical values to determine whether to reject the null hypothesis. If the test statistic is to the side of one of the critical value, then we need to reject the null hypothesis. This is hypothesis test. In control charts, the upper and lower control limits, UCL and LCL, are kind of equivalent to the two critical values in the hypothesis test. The upper control limit is the process mean plus the z value with the probability of the sample standard deviation at half alpha confidence. And the lower control limit is the process mean minus the z value with the probability of the sample standard deviation at half alpha confidence. If the control chart has 3 sigma limits, then z half alpha is 3. That's the distance from the center line to the upper and lower control limits. The two types of errors in a hypothesis test have corresponding meaning in analyzing a control chart. Type 1 error alpha is the probability that we reject the null hypothesis when we actually shouldn't. It's analogous to false alarm on control chart. That is, a point lays outside control limits, but the process is truly in control. Type 2 error beta is the probability we fail to reject the null when we should. It's analogous to insensitivity of control chart to problems. Points lay inside controlled limits, but the process is nevertheless out of control. Given we have hypothesis tests, why do we need control charts to help detect the errors? Because hypothesis test only allows us to test the hypothesis about the parameter value or a similar hypothesis statement, while control charts may give us more information on non-random patterns, trend, the performance along the time as a time series data set, or other information that may lead to some causes of the problems. We have choices of control limits, not only using 3 sigma control limits, although the 3 sigma control limits are the most popular ones. So there is a trade-off between wide or narrow control limits. Wide control limits can reduce false alarm, but increase the risk of insensitivity. Narrower control limits, on the other hand, reduce risk of insensitivity, but increase risk of false alarm. So to make right control limits is important. Here are 2 consequences of incorrect control limits. First, too insensitive, or when beta is too big. A control chart never finds anything wrong, but the process produces bad products. Second, alpha is too big, or too many false alarms. So the consequences is too many false alarms destroy people's confidence of using the control chart. So those are the similarities between hypothesis test and control charts. Let's look at the differences between them. Let's summarize the differences in viewpoint between test of hypothesis and control charts. So we use hypothesis test to check validity of assumptions such as actual process mean or variance. And we use control charts to detect departures from assumed state of statistical control. Using hypothesis test, we test the sustained shift. For example, if we have actually reduced the variation like we think we do, while using control charts, we detect different types of shifts and trends, short-lived shifts, steady drifts, or trends for a potential shift. So those are different viewpoints. An example of determining control limits given a false alarm rate. When a process is in control, a dimension is normally distributed with mean 30 and standard deviation 1. So those are the process mean and standard deviation. Suppose sample size is 5. Find the control limit for an X-bar chart with a false alarm rate of 0.0027. The variable X is the dimension of the part. It follows a normal distribution with mean as 30 and standard deviation as 1. The X-bar is the sample mean dimension of the part. So X-bar follows a normal distribution with mean as 30. The same with the process mean, but the standard deviation is 1 over square root of sample size 5. We want to find the control limits for an X-bar chart. So we need to use the statistics of the sample of X-bar to build the control chart. Remember that we have talked about the difference between the distribution of individual measurement X and the distribution of sample mean X-bar. The sample size plays an important role in this difference. Using the equations we introduced on slide 60, we can find the upper and lower control limits of these X-bar control charts. Given that false alarm rate, or alpha, is 0.0027, as the dimension of the part can either too large or too small. So it's a two-sided problem. We need to find half alpha. So half alpha is 0.00135. This value is the probability that X-bar is larger than upper control limit. And also, it's the probability that X-bar is smaller than the lower control limit. As every X-bar has a corresponding Z value on standard normal distribution, and every upper control limit has a corresponding Z value on standard normal distribution too. So the probability of X-bar exceeds UCL is the same with the probability that the z exceeds this value. This is the upper control limit mapped into the standard normal distribution. Therefore, given phi z is 1 minus this probability, which is this value, 0.99865, then we find the z value is 3. That is using the probability of z to look up the z value. So this is again a 3 sigma control limit. So we find the upper and lower control limits using the equations, plug in the values. So which are the 3 sigma away from center line. What if we change the false alarm rate? How will the control limits change? So this time we set the false alarm rate as 0.005 instead of 0.0027. Then half alpha is 0.0025. So z half alpha is 2.81. And then the new control limits are narrower. If the control limits are not 3 sigma, they are called probability limits. Let's briefly review the general model of short control chart because they are also applied to X-bar chart and R chart. If X is a quality characteristic, W is a sample statistic of X, then the control chart mean is mu W, standard deviation is sigma W, and the upper and lower control limits are mu W plus and minus L times sigma W. L is the distance of control limits from center line. How many standard deviation? This type of chart is called short control chart. Given that the general model of short control chart, as we know that the sample, statistic, and control chart heavily depends on the sample size. Let's look at how the samples be selected to detect shifts due to assignable causes. In other words, we need rational subgroups to make our quality control more efficient. First, when we select the samples or subgroups, we want to maximize the chance for differences between samples and minimize the chance for differences within a sample. Second, we use consecutive units of production. Third, we desire small sample size so that new events won't occur during the sampling. Inspection is not too expensive, but the size should be still large enough to ensure normal distribution. And why do we need both X-bar chart and R chart? Why don't we just use one of them? So here's the answer. When we monitor a process, we monitor it through monitoring its statistics. There are at least 2 statistics we care, the process mean and process variability. Why do we need to monitor both? Here it shows us the reason. If the process is doing okay, this line, both the mean and spread are relatively stable. Here, there may be some small shifts or variation, but they're acceptable. They are due to chance causes. So, but if there is a mean shift in the process, we can observe that the mean jumps here and there, but the spread seems stable. And if there is an increase in process variance, although the mean stays stable, the distribution becomes wider. These 2 situations both indicate some assignable causes in the process. Therefore, we use both X-bar chart and R chart to monitor both mean and variability of the process. X-bar charts show us if the mean shifts, and R charts show us if the variability is okay. Before we continue to learn the statistical basics for X-bar chart and R chart, let's first review the relevant terminology. There are two causes of variations: assignable causes or special causes keep the process from operating predictably. Those are the things that we can do something about. Chance causes or common causes are random, inherent variations in the process, so we may not eliminate them. And there are two means of control: in specification and in statistical control. In the meaning of in specification, in control means the process meets customer constraints on product, so it meets some external demand. In statistical control, on the other hand, in control means no assignable causes of variation present in the process, so it meets some inherent statistical standards. So they are kind of independent ideas. For X-bar chart, for quality characteristic X that follows normal distribution, if x1 to xn is a random sample, then x bar is the numerical average of x1 to xn. And x bar follows a normal distribution with the process mean and the standard deviation over square root of n. Type 1 error probability alpha is the chance of x bar either above the upper control limit or below the lower control limit. In other words, the probability that x bar is within the control limits is 1 minus alpha. So in phase 1 of control charts application, we must estimate mu and sigma from data in an in-control status of the process. If the process is already out of statistical control, then our estimation of mu, sigma, and control limits cannot be correct. Then statistics of the range, the R chart. R means the range is a sample statistic. Remember in chapter 3, we introduced the several statistics to reflect the spread of the several measurements to reflect the spread of a distribution, including range, standard deviation, and variance. Range is one of the measurements to show the spread. There is a relationship between range and standard deviation of a sample, defined in the assumption that this is a normal distribution. That is, the estimated standard deviation is the range divided by D2, where D2 is a function of sample size n and can be found in Appendix 6 of our textbook. Appendix 6 lists the factors for constructing variables control charts. We can get a better estimate for sigma if using more samples. We compute the range of each of the m samples and then compute their mean, the R bar. Using R bar, we may get a better estimate sigma. When using these equations to compute control limits in phase 1 control chart usage, the control limits are trial control limits. Let's compute trial control limits for X-bar chart. Assuming for quality characteristic X, we take m samples. M is no less than 20. For each sample, the sample size n is either 4 or 5 or 6. For any sample I among the m samples, there is an X bar I and Ri. So for m samples, we have X bar and R bar as the average of the m. We use X bar as the center line of the X bar chart and use R bar and the factors in Appendix 6 to compute the control limits of X bar chart. The key factor is D2, lowercase d2, and capital A2. We look up these values using the sample size n. Next, R chart. X-bar chart and R chart should be always used in pairs to monitor the mean and variability of a process. The general model for R chart is the same as short control chart. That is, the center line is the mean of R, and control limits are the mean of R plus and minus a distance L multiply the sigma of R. If we use 3 sigma limits, then lowercase d3 and lowercase d4 in Appendix 6 are the factors help us identify the control limits. Just remember these equations. And here's the relation between capital D's and lowercase d's. Both capital D's and lowercase d's are given in Appendix 6. We need the sample size n to locate the correct value of d's. Pay attention, this n is the sample size, not the number of samples m. R chart is quite sensitive to departures from normality. So if the quality characteristic is not quite normally distributed, then the R chart may vary a lot and cannot give us accurate information. Or if the sample size is too small, usually smaller than 4, then the R chart may not be quite informative either, because too small sample size means is not quite normally distributed. Pay attention, Appendix 6 only gives us the factors for the 3 sigma limits computation. If the X-bar chart and R chart do not use 3 sigma limits, then these numbers are not correct. To make good samplings, here are some guidelines. First, sample size should vary between 3 and 8. Usually, 4 to 6 is more common. Remember the criteria. We need to have relatively small sample size to reduce the sampling cost. Meanwhile, maintain each sample as normal distribution. So, in general, 3 to 8 is a good sample size. Second, sample must be homogeneous, which means we collect the data in each sample at the same time, or in other words, they are consecutive units. Using the same raw material with the same operator collecting them, using the same machines, etc. In other words, remove all other differences in operations as much as we can. Third, time may pass between samples, but not within samples. Again, this is to minimize differences within each sample, while allow some necessary differences between samples. There are steps we need to follow to build trial control limits for X-bar chart and R chart. First, we start with 20 to 25 samples. This 20 to 25 samples, this 20 to 25 is the number of samples, m, not the sample size n. Then we use all data to calculate initial control limits, which means maybe some of those data are out of control data. But in this step, we do not know, and we use all of them. Then we plot each sample in time order on chart. Plotting each sample means for each sample, there is 1 X-bar and 1 R. We plot the X-bar as 1 point in X-bar chart and the R as 1 point in the R chart. So 20 to 25 samples means we have 20 to 25 points in X-bar chart and in R chart. Next, we check. We check for out-of-control sample points using Western electric rules or other sensitizing rules. If there's any out-of-control point found, then we investigate the process, remove the assignable causes, and remove the points due to the assignable causes, and then use the rest data, which are all in control data, to recalculate control limits. If we cannot find assignable costs for the out-of-control points, we anyway need to drop those points and recalculate the control limits, because no matter we find assignable costs or not, those points are out-of-control points anyway. So we need to drop them when recalculating the control limits. Here are the 4 Western electric rules we learned in Chapter 5. After applying them to identify any out-of-control points, the major job is to investigate for assignable causes. Here are some examples of out-of-control status of X-bar charts. The first one is 1 point outside the control limits. The second one is 8 consecutive points on one side of center line. The third one is 2 out of 3 consecutive points beyond 2 sigma warning limits on one side of center line, on the same side of center line. And the last one is 4 out of 5 consecutive points plot beyond 1 sigma warning limits on the same side of the center line. Here are additional sensitizing rules. We must use them for some we may use them for some special industries or processes, but the 4 Western electric rules are the most general ones that can be applied to all processes. From slide 86 to 89, we summarize once again what we have learned about the X-bar chart and R chart. Please read through them. Then, the X-bar chart and R chart are used when sample size is between 3 and 8. Next is another pair of charts, X-bar chart and sigma chart. These charts are used when sample size is greater than 10. Remember, we talk about sample size. We desire relatively small sample size, but still maintain a normal distribution for each sample. However, for some processes, to maintain normal distribution, or because of the nature of the sampling cost, we may have sample size greater than 10. So this X-bar and sigma charts are for that situation. And there are 2 situations. Situation 1, if we do not know the standard deviation of the process. What we have is some samples, and we can use the samples to get some sample standard deviation S bar. Then we can use the equations here to calculate the control limits of X-bar chart and sigma chart. Again, only if we use the 3 sigma control limits can we use Appendix 6 to look up the factors A's and B's based on the sample size. Situation 2, if we do have historic data and we know the process standard deviation sigma, then here are another bunch of equations for us to calculate the 3 sigma control limits. When construct X-bar and sigma charts, first, we need to make a judgment whether it's situation 1 or situation 2, whether we know the standard deviation of the process or not. Then we choose the right equations to calculate the control limits. So homework 4 is due on Friday, July 15th.